So we've seen already some notions of rank for tensors and polynomials and how things of high rank have some special properties. And over the last few years, I've been thinking about this kind of thing quite a bit, and especially what happens in like a limiting case where the rank actually becomes infinite, which only happens in infinite situations. And so I want to say just a few things about this kind of situation in this talk. So I'm going to talk about like three different but related things. So I'll break the talk into three parts. So to begin with, I want to talk about some of the ideas that went into the proof of Stillman's conjecture. And so Stillman's conjecture itself is not, I'm not really going to say much about it, but I guess I'll start by just stating it so you at least know what the statement is. Okay, so it says that it's just some bound, which depends on two parameters, I'll call it D and R, such that if you have R polynomials in some number of variables, and I'll just work over the complex numbers for simplicity. So you have these R polynomials, and that's what this R is, and their degrees should be bounded by D. And they should be homogeneous. And the conclusion is that the projective dimension of the ideal they generate is bounded by this bound. Okay. And if you don't know what projective dimension is, it doesn't really matter so much. It's just, you can think of it as some measure of complexity of these polynomials. So what this is really saying, the important thing here is that this bound does not depend on the number of variables. That's really the whole point of the conjecture. And so what this is saying is that in this regime where like the number of variables is growing, but your degree is bounded, this measure of complexity doesn't grow. Okay, so this was proved. It's proved now. It was first proved by Danelon and Hoxter in about 2016, and then Harman and Sam and I proved it again. We gave two proofs actually a few years later. And we use this idea of going to infinity, which is I'm going to tell you about in just a second. And then a fourth proof was actually given by Drysma and Zone and Vick. Okay, and in all these proofs, there's some idea of like of rank figures in an important way. So let me tell you what kind of rank. So the strength of some polynomial.
But can I ask a naive question?
Yes.
So the size, the length of the resolution boundaries, can you also bound like the size of the things appearing?
No.
I see.
But there's other things that you can bound.
You really can't. Like
I don't think so.
Okay.
I guess maybe I'm not sure. I shouldn't say. I don't know offhand. There's other things you can bound, like the regularity. Okay. Okay, so the strength of some polynomial is the minimal S, such that you can write it as a sum of S things of lower degree, product of S things of lower degree. So here, the degrees of these guys, strictly less than the degree of that. So this word strength was introduced by Danelon and Hoxter, but this same idea was considered earlier by Schmidt, and this is also called the Schmidt rank of F. Yeah, so this is some notion of rank essentially for polynomials or symmetric tensors. And a slightly, well, like a generalization of this, which is kind of useful to have, is I'm going to define the collective strength of some tuple of polynomials to just be the minimum strength of a homogeneous linear combination. So a non-trivial homogeneous. Okay, these should be homogeneous elements to begin with. Okay, and what this means, non-trivial is just, not all the coefficients can be 0. And homogeneous linear combination means that, so the coefficients are singulars, not polynomials, just complex numbers. And homogeneous means that you only take things of the same degree and look at linear combinations of them. So like the things of degree 2 and the things of degree 3 in this list just like completely don't interact for the purposes of this definition. All right, so the really kind of key thing, let's call this the key insight that Danelon and Hoxter had in their proof of Stillman's conjecture, is that if you have some polynomials of high collective strength, these guys have high collective strength, then they behave approximately like independent variables. Okay, and they proved several, like, this is kind of a general principle. It's not a precise statement, but Danelon and Hoxter proved several precise statements that kind of fit this pattern. So for example, if the collective strength is high enough, then these things will form a regular sequence. One precise statement. So anyway, our idea of Harman and Sam and me, our idea was to try to take a limiting form of this statement, right? So like here, as the collective strength gets higher and higher, they behave more and more like independent variables. This approximation becomes better. So if you could pass to some limiting situation where the strength was like infinite, you might get some like really nice statement. And that was our idea. So we want to pass to a limit. Strength is infinite. Okay, well, strength of polynomials is always finite, so you're not going to see infinite strength ever by thinking about just polynomials. And so you need to consider some kind of infinite series that like see any kind of infinite strength. So we're going to consider the following ring. I'll call it R. So this is going to be a graded ring. And the degree D piece is just going to be like all like series of degree D in infinite linear variables. So it's formal C linear combinations of degree D monomials and some list of variables. Okay, so for example, you could look at like the sum of all D powers. Okay, so this is an element in this ring, and this element has infinite strength. Are there any questions so far? Definition of this ring. Okay. This is actually, yeah, I should say this is a ring. You can multiply these kinds of infinite sums like this, and it works out fine. Okay, so the theorem that we proved. So if you sort of buy that this principle would apply to these things, which are not actually polynomials, but sort of similar to polynomials, it might suggest that if you have R of these series that have infinite collective strength, then they literally should be independent variables in some sense. And that's basically what we proved. We proved that this ring R is abstractly a polynomial ring. So maybe I should say is isomorphic to polynomial. And well, there's uncountably many variables in this polynomial ring in every degree. The way that you kind of get the variables for this ring is you take a maximal collection of elements of infinite collective strength. Those will be the variables. So something like this might be one of the variables in the description of this as a polynomial ring. Okay, and the proof of this theorem is actually, once you know the idea, it's really easy. So let me kind of say what the key idea is. So let's say that we have some graded ring S. So we say that a graded ring S has enough derivations, if whenever you have some element of positive degree, it's not 0, then you can find a derivation that doesn't kill it, or really a derivation of negative degree that doesn't kill it. So then there exists a homogeneous derivation of the ring of negative degree. Doesn't kill it. So if you think about like if S is just a polynomial ring, if you have a non-zero polynomial of positive degree, it's not killed by some partial derivative. So you can just use partial derivatives, and that shows that those rings have enough derivations. And we proved that the converse is true. So theorem, if S has enough derivations, then S is a polynomial. And the proof of this is basically an exercise. It's really quite easy. You just kind of pick a minimal set of generators, imagine you had a relation, and then hit that relation with a derivation to make a lower degree relation, and you get a contradiction by some deduction. And then that proves this theorem because it's easy to see that this ring R has enough derivations, because again, you can just use like partial derivatives. Okay, so yeah, this is kind of what I wanted to talk about as far as Stillman's conjecture goes. So I guess the point here is that Ananya and Hoxter had this realization, and for them to prove kind of any instance of their principle, it was like really hard. Like all the theorems in that paper are quite difficult. But this limiting form that you kind of get by looking at the results is actually quite easy to prove. And you can then go back. You can go from this limiting form back to finitely many variables. And so that's how we proved Stillman's conjecture in our paper. First gave like a really easy proof of this limiting statement, then said that you can go back to finitely many variables. And that leads to a much cleaner proof in the end. Okay, so yeah, when you have this like infinite variable setting, you get these really, at least in this case, this really clean result that you actually just literally get a polynomial ring, and it's really useful to kind of think in those terms. Okay, so yeah, so this shows that like these infinite strength things are kind of building blocks for everything in this ring. But so far we haven't really said anything interesting that distinguishes different things of infinite strength, because so far they all kind of look the same. And so you might wonder about like the internal structure of an infinite rank thing. And that's the next kind of topic that I want to talk about.
Sorry, is there some way I can think about strength in terms of derivations?
Well, yeah, I mean, you can say things about like there is a connection, but yeah, let me not try to say what it is now. Okay, yeah, so all right, so I want to now talk about like, yeah, some properties of infinite, like individual infinite strength elements. And for this, it'll be kind of convenient to repackage these things in a slightly different way. So let me make a definition. So I'm going to define a D space as a vector space, and we'll just stick over the complex numbers, equipped with a symmetric D multilinear form. Okay, so you have something like this. Okay, so like when D is 2, this is a really familiar thing, right? You just have a vector space with a symmetric bilinear form. And those are pretty easy to understand. But already when you get to D equals 3, you have like trilinear forms, which are really weird. And so this, I mean, these things are basically the same things as the elements of our D. So if you work with like a countable infinite dimensional vector space, then if you want to give one of these things, you just have to like specify all the pairings and the basis vectors, and sort of by polarization, you can convert that into a polynomial. So giving, I'll use omega as notation for the form. So giving omega is equivalent to giving an element of this degree D piece of this ring. Right? So you can really just think of these elements, these kinds of infinite series. And there's two ways that you can actually generalize this, which is actually what I prefer to work with, but I'm just going to stick with this kind of simple setup for the talk to make things not too confusing. So one thing that you can do is you can, instead of just having a single form, you can have some finite list of forms. And the other thing that you can do is, instead of making the form symmetric, you could make it interact with the symmetric group in a more interesting way. So like you could make it alternating, or you could use a Schur functor here, like a general Schur functor instead of just the symmetric power. And basically everything I'm going to say is going to work in that generality where you have some finite list of things with Schur functors, but I'll just stick to this for the talk. All right, so one of the nice reasons for introducing this definition, going to these spaces, is that there's an evident notion of map for these objects, right? Like if you have two D spaces, you can talk about like an embedding of one into the other. That should be an injective linear map that respects the form. And so, so I want to talk about like two properties, basically, of D spaces. And the first, here's the first one. It's going to use this idea of embedding. So we say that a D space B is universal if every finite dimensional D space embeds into it. Okay, and here's an example. It's not so hard to write down an example of a universal one explicitly. So if we take V just to be C infinity, and well, let's take V equals 3 to be concrete. And we take our form to be, I'm just going to write down like the sort of polynomial corresponding to it, just xi, yi, zi. This is universal. And the reason is if you imagine some finite dimensional space W and you want to embed W into V in a way that respects the form, you can kind of do the dual thing, like think about a linear map from V dual to W dual. And you just need to find such a linear map such that this form specializes to the given form. And since you have like all these terms with distinct variables, everything's very independent. So you can just map one monomial to each monomial here to a corresponding monomial here. So it's very easy to define the right kind of linear map. Okay, so these things exist. But what's more interesting is this theorem has Ziegler. And well, then kind of an upgraded version by Danelon, Dreismann, Egmont. Which says that if you have any D space, then it's universal if and only if the form on it is of infinite strength. Okay, so Kajla and Ziegler proved like the version I stated, and this more general version is when you have like multiple forms, some lambdas or whatever. And this is a really cool theorem because it means that as long as you have infinite strength, you can sort of find everything inside of it. Infinite strength forms just kind of see everything. Okay, so this universality is like the first property I wanted to isolate. Here's the second property. We say that a D space V is homogeneous if the following condition holds. So whenever you have two finite dimensional subspaces, okay, so these are just like finite dimensional linear subspaces. You can restrict the form from V down to these subspaces, and so these have the structure of a D space. Then any abstract isomorphism between these two guys actually extends to an automorphism of V. Okay, so for example, if you think about the case where these subspaces are one-dimensional, just like spanned by a single vector, then the only information there is like the norm of that vector. Like you just plug that vector into omega, you get some number. And so if the two vectors have the same norm, then well, the one-dimensional spaces they span are abstractly isomorphic. And so this is saying that there should actually be an automorphism of V that induces that isomorphism. So what that really says is that the automorphism group is going to have to act transitively on the set of vectors of a given fixed norm. Okay. And this is actually kind of a familiar notion. So for example, Witt's theorem about quadratic spaces says that if V is a finite dimensional, non-degenerate quadratic space, so in my terminology, a two space, a symmetric bilinear form, then V is homogeneous. Right? Witt's theorem says that the orthogonal group acts transitively on vectors of a given norm. And you wouldn't really expect homogeneity for any other like D spaces in finite dimensions. Like if you think about a cubic space, right, something with a trilinear form, that's not really going to have any automorphisms. Automorphisms will always be pretty small, and you're never going to get this kind of thing. But what's really cool is the next theorem, which says that you do get this property in infinite dimensions. So the theorem, this is a theorem of Nate Harman and me, says that there exists a countable dimensional universal homogeneous D space. And furthermore, it's unique up to isomorphism. Okay, so let me say a few things about this. So first of all, it's important that the word universal is here, because if you just took like a space with the zero form, that would be homogeneous, right? So there are these like really obvious degenerate examples. So this is saying that it's a really interesting example and also homogeneous. And it's unique up to isomorphism, and I think that's really crazy. Like I completely wouldn't have expected a result like this. It's saying that there is a like distinguished tensor in infinite dimensions.
Is that it up there in the tweet?
No,
I see.
no, that's not it. Yeah, so for the cubic one, I don't know how to explicitly write it down. If you write down a cubic such that the coefficients are algebraically independent over Q, that will be it. So it is kind of a generic condition.
So which coefficients are like in?
Oh, sorry, like a general cubic, and all the coefficients are algebraically independent. Yeah. But I don't know a more explicit way to write down the cubic case. Yeah, and I think one of the reasons that this result was kind of so unexpected to me was that I'd mostly been thinking about these kind of tensors from the point of view of commutative algebra or algebraic geometry. And the proof of this really uses ideas from model theory. So it's just like a completely new phenomenon that like wasn't on my radar at all. So I want to say a little bit about at least some of the ideas in the proof and how model theory figures in, because I think that's kind of an important theme about these infinite dimensional tensors. So really there's an analogy. This is a really important point, I think. So there's an analogy between relational structures and, well, these D spaces, or tensors if you prefer. So let me say what I mean by this. So relational structures are the kind of things that are thought about in model theory. So a relational structure is just a set equipped with some relations. So you might have a set with a binary relation, and you can like represent a graph as like a set with a binary relation, right? Like you have edges and they're connected or not. Or you could represent like a total order or a partial order with a binary relation. You could also consider like higher arity relations. Like you could have relations that take 3 inputs and represent things like hypergraphs using that setup. And a relational structure might have more than one relation. So you could have a 2-area relation and a 3-area relation. And if you think about like if you have a set X, then like a binary relation on X is the function from X times X to true or false. And like the point here that I want to make is that the linear analog of this is a bilinear form. This is analogous to B is a vector space, and we have a map B tensor D to B space. Okay, and so this is really useful because you can now like look at all this work that people have done in model theory and try to translate that back to our setting where we have tensors, and you can make similar definitions and try to prove similar theorems, and that's really what we're doing here. So let me tell you the sort of the classical model theory version of this result. So if you have, if C is, let's say, some class of finite relational structures. Okay, so the finite here means that the set itself is actually finite. So you should think about like graphs with finitely many vertices or totally ordered sets with finitely many elements or something like that. Then under some conditions on C, you can form a limit of C. There's like some kind of limiting object. And this is called the Frisé limit. Okay, and my co-author here, Nate Harman, was here and spoke in the learning seminar a few weeks ago, and I think he talked a lot about this. So if you were at that talk, it's this thing. And this Frisé limit it always has this homogeneity property. So that makes sense for these relational structures. It's the same definition if you have two substructures, and any abstract isomorphism comes from an automorphism. So this method of Frisé limit is like a way to produce these homogeneous structures. So for example, let me give two examples of this. So the easiest one to understand, it's still a little bit interesting, is if you take C to be the class of all finite totally ordered sets. Okay, so in this case, this Frisé limit exists, and the limit is going to be the Frisé limit is always a countable object, so it's going to have countable cardinality, and it has a total order on it. And well, it's Q. It's Q as a totally ordered set. Okay, and so the key point here is that if you imagine two finite subsets of Q, which are abstractly isomorphic as totally ordered sets, then you can find an automorphism of Q that preserves the order that moves one set to the other. And that's pretty easy. There's lots of automorphisms of Q that you can make because you can just use like piecewise linear maps. That'll let you move anything to anything else. Okay, so this one's like really easy to just like do by hand and picture in your head. Here's the more complicated one. If you take C to be the class of all finite graphs, then the limiting object is this thing called the Rado graph. And the Rado graphs, if you look at Wikipedia, there's like actually kind of concrete descriptions of it, but I don't know how helpful they are. But it's basically the unique homogeneous graph that has every other graph inside of it, universal homogeneous graph. It's also called the random graph because if you just take a countable set of vertices and connect edges with probability 1/2, you almost surely get this graph. But this homogeneity property ensures that it has a huge automorphism proof, right? Like, for instance, it's edge transitive because if you have two edges, they're abstractly isomorphic as graphs, and so you can move one to the other. Okay, and so that's how we prove this theorem. So the proof is we basically take a Frisé limit. We take like the Frisé limit of the class of finite dimensional D spaces. And like the classical Frisé limit setup really works with finite relational structures, and so we have to do some modification of the machinery to actually make this work, but it's basically the same idea.
describe.
What?
It's also hard to describe.
The Rado graph?
No, I mean this.
This thing? Yeah, I don't know an explicit description in the cubic case. Here, let me say one thing that at least make it a little bit more concrete. So when I visited here in September and met with Jan and Arthur, and we figured out what the case of a pair of quadratic forms look like. So this isn't like officially written up or anything, but this is the answer that we came to. So if we consider, so the universal homogeneous 2-2 space, so this is vector space with a pair of symmetric bilinear forms. So we're in countable dimensions, and a symmetric bilinear form you can think of as a symmetric matrix, infinite by infinite, and there's no like finiteness conditions, like you don't have to have almost all zeros in any direction or anything, so it's just two symmetric matrices. And the condition is that, so it's given by a pair of n by n symmetric matrices. And the condition is just that the columns of these matrices should be linearly independent. Okay, so you can only do this in infinite dimensions, right? If you imagine in n dimensions, if you had two n by n matrices, you can't make all the columns linearly independent because there's two n columns. But when you go to infinite dimensions, there's plenty of room for this. And so like you could take one of the matrices just to be like the standard diagonal matrix, and the other matrix just has to have the property that like, you know, no kind of finite vectors in the column space. And it's not really obvious, I think, that you're only getting one isomorphism class here, right? But that's part of the theorem.
So in this cubic case, how do you see this one as not?
I don't know if it's easy to do directly, but the last thing I'll say will make it more clear. Yeah, let's look at there.
So maybe you could say how in this concrete case, how kind of the infinite general linear group or so acts on these objects.
I mean, the general linear group acts on symmetric matrices just in the usual way, like G and G transposes.
Yeah, but it's not that. I mean, it's. It's not a general linear group.
Right.
Union of finite.
That's right. So when you're in this infinite setting, there's various versions of the infinite general linear group that you might think of. And the correct one here is actually the full automorphism group of your space, which is not the union of GLNs. So maybe that was another reason why this was a little mysterious, like when stuff Jan and I had previously done, we've always been thinking about unions of GLNs, and that's just like the wrong group for this kind of stuff. All right, but that's a good question, because the next thing I want to talk about, I want to say a little bit about what the automorphism groups of these things look like, because homogeneous things always have really big automorphism groups. They're usually really interesting to think about. So let me call GB the automorphism group of this universal homogeneous space. So this is sitting inside this infinite general linear group, this version of all automorphisms. So for example, G2, so when B is 2, we have symmetric bilinear forms, and this is just the infinite orthogonal group. And G3 is like some infinite dimensional Lie group, and it's like the infinite orthogonal group, but it's associated to trilinear forms. And I think it's just like amazing that such a thing exists, right? There's nothing like this in finite dimensions. This is, you can only see this in infinite dimensions. It's really kind of a fascinating group. We know very little about it. And so Nate and I know like the algebraic representation theory of this group, and it's very similar to the algebraic representation theory of O infinity. But beyond that, we don't really know much. And there's all kinds of interesting things that you could try to do. Like you could, see if there's a notion of like Cartan subgroup, file group, Dinkin diagram, like all kinds of things you could ask. I don't know anything yet though. But these groups are pretty big. You know that they have to be pretty big by the homogeneity property, right? Like they act transitively on vectors of a given norm. But I want to introduce like another concept to really kind of quantify how big these are, and also to connect back with some classical topics and model theory. So I'm going to make a definition or two. This first one, well, it was Peter Cameron who came up with this name, but I think people had thought of the concept before him. So if X is a set, and G is a subgroup of the symmetric group on this set, so the group of all permutations of X. Then we say that G is oligomorphic. If it has finitely many orbits on every power of X. Okay, and basically, if you have a homogeneous structure, its automorphism group is almost always oligomorphic. So in particular, like the automorphism group of the Rado graph. Acting on the set of vertices of the graph. So in that case, if the homogeneity property, this kind of explains why it's oligomorphic. If you look at x to the n mod g, if you think about x to the n, you have n vertices, like let's just imagine they're distinct. And so you can look at the induced graph on those n vertices. And the homogeneity property says that if you have two sets of n vertices that make the same graph, they're in the same orbit. And so this is really just going to be like isomorphism classes of graphs with n elements, which is fine. All right, so Nate and I came up with a linear analog of this definition. So now V is a vector space, and G is some subgroup of GLV. So we say that G is linear oligomorphic. Yep. Well, we basically just use the analogous condition, but you have to say it slightly differently. So the statement is if for every n, that's like the x to the n that we're looking at, there exists some finite dimensional subspace. Such that if you have any subspace of dimension n, you can move it into E. The group. And maybe a better way to say this, like intuitively, but less rigorously, is the condition is really saying that if you take V to the n mod G, that should be like a finite dimensional space. Okay, that's really the idea. Okay. And so this gets at, okay, well, let me state a theorem first. So the theorem that we prove is that this group here is linear homomorphic. And it's really this theorem that motivated all this work by me and Nate. So we had a previous project where we were looking at just these classical oligomorphic groups, and we like did some representation theory with them. We made some really cool tensor categories using these things. And we thought that there should be some similar story in this linear oligomorphic case. We had an inkling that there should be such a class of groups, first of all, and what we did in the oligomorphic case should extend. But it's really not easy to write down any examples of really oligomorphic groups or linear oligomorphic groups explicitly. Like you always need to rely on some existence of homogeneous structures. And so, yeah, this project was basically, we were motivated by trying to find examples of linear oligomorphic groups. And so this theorem gives you a bunch of examples. So what we want to do next in this direction is to like try to do this representation theory stuff, and we haven't been able to do that yet, but that's where we're going. Okay, so I want to say one more thing in this direction that gets in a little more into the model theory side of things, because I think there's a lot of interesting questions there about model theory of tensors, and I just want to say one just so you have an idea of what I'm talking about. So another definition. So this is an important definition from model theory. You say that a relational structure is called Omega-categorical. If it's countable, and let me just say determined by its theory. Okay, so the theory of a structure is just like the list of all sentences, like logical sentences that are true of that structure. And so what this is saying is that your structure is Omega-categorical if you have any other structure that's also countable, and it has like the same list of true statements, like you can find an isomorphism between them. Okay. And if you imagine like some crazy infinite graph that, oh, I shouldn't say random because the random graph is the Rado graph, which is really nice, but one that's not nice. Like, you know, it's good. There's too much data there to kind of determine it from its list of its theory. So it's not going to be Omega-categorical. But these homogeneous ones tend to be Omega-categorical. So like the red Rado graph is. And you can make a linear analog of this definition. So Nate and I formulated something that we called linearly Omega-categorical. And I mean, essentially you change countable to countable dimensional. And that's more or less the idea. And so we proved that this thing does have this property. So the universal homogeneous D space is linearly Omega-categorical. Okay, but there are other examples. In fact, like if you just take, I think maybe every quadratic space is linearly Omega-categorical of countable dimension. So there's plenty of other examples of these things. And I think an interesting problem is to try to characterize these linearly Omega-categorical spaces. The reason I think this is an interesting problem is that there's a classical version of this result, of this problem that has a very nice solution. This is the theorem of real, say this name, Narjuski. Which basically says that if X is a countable structure, then X is Omega-categorical, if and only if its automorphism group is oligomorphic. Okay, and this is really like a theme in this kind of model theory where like you can, like a lot of model theoretic properties that can be encoded in the automorphism group. And so I think it'd be interesting to explore that idea in like the tensor setting. So I mean, you can make a direct analog of this statement, right? If you think about these D spaces, you could say that linearly Omega-categorical should be equivalent to the automorphism group being linearly oligomorphic. That's maybe a reasonable conjecture, but I don't have any idea about if it's true or not. Okay, so that's the end of the second part. Any questions? Okay, so the last part is going to be a little bit shorter. It's also going to be about these symmetric D spaces. So obviously an interesting problem is to try to classify these things. And I think it's probably too hard, right? You're not going to give a list of isomorphism classes of these kinds of things. But in infinite dimensions, there's a weaker notion than isomorphism that you can consider, which I call isogeny. So we say that V and W, these are two D spaces, are isogynous if there exist embeddings in both directions. Okay, so obviously if you're in finite dimensions, if you have embeddings in both directions, the dimensions have to be the same and then they're isomorphisms. So the definition doesn't even really make sense there. But it is an interesting thing in infinite dimensions. And a really cool theorem is the following. So let me call XD the set of isogeny classes of countable dimensional D spaces where the form has infinite strength. Okay, so this is a partially ordered set where you say one thing is less than another if there is an embedding. Right? This is basically defining a quasi-order, and here we've killed the equivalence relation. And a theorem of, well, it's from the same paper of Dick, Dresma, Danelon, and Hagerman, says that this partially ordered set XD has a unique maximal element and a unique minimal element. And so this suggests that, you know, this could be an interesting object to study. This is really one very nice feature of it. And, so you might ask, like, what's the structure of this poset in general? And well, I don't know the answer in general, but the first interesting case is when D is 3 and Arthur and Alessandro Danelon, me solve that case. we showed that X3 is, as a post set, it's isomorphic to n union infinity. And let me explain how this isomorphism works. It's really quite concrete. So let's call Q the degree 2 part of this ring R I was talking about. So this is just all quadratic expressions and these x1, x2 variables and so on. And inside of this, I'll call QF the subset of things of finite strength. Okay, so if we have a cubic, let me go over here. So let's say that omega is some kind of cubic form. So we can look at its partial derivatives. And these are going to be degree 2 things. And we define, so here's the definition. So we call this the residual rank, or K. So the residual rank of omega is defined to be the dimension of the span of these partial derivatives, but in this quotient space where we kill the forms of finite strength. Okay, and so for example, let me do 1 or 2 examples. So if you take the simplest cubic form, this diagonal one. So if I take the partial derivative of this, this is just, it just has 1 term, and this has finite strength. This is strength 1. So this does belong to this finite strength subspace. And so in this quotient space, this just becomes 0. And so all these partial derivatives are 0 in the quotient, and that means that the residual rank here is just 0. So if you want to have an example of positive residual rank, you have to do something like the following. So we could take omega to be, all right, let me use a new set of variables to make this look a little nicer. So we could start with this and then add on this term. Okay, and this has infinite strength because this first part makes infinite strength. But if I take the partial derivative with respect to the z variable, I get this infinite rank quadratic form. And so that's not 0. And this thing does have residual rank 1. Okay, and that's what induces this isomorphism. So if you have a cubic space, you look at the residual rank, and that lives in here, and that makes this isomorphism. And the proof of this theorem is it's kind of a long exercise in using this theorem on universality of Constante. Basically, that theorem says that if you have some like nice D space, you can sort of ask it for vectors that have properties you want, and the theorem says that you can find those vectors. And you just kind of keep doing that to build embeddings. So here's the, let me just end by drawing a little picture. So this is like the landscape of cubic spaces. Okay, so there's some like big part where you have all the finite strength things. This includes all the finite dimensional ones. And then there's some other part where you have the ones of infinite strength. And the ones of infinite strength are partitioned into these isogeny classes that we've been talking about. That's parameterized by n union infinity. So this is residual rank 1, or 0, and residual rank 1. And you kind of keep going, and you get out to residual rank infinity. And inside of each other, so there's a bunch of isomorphism classes here. Inside each one of these isogeny classes, there's a bunch of isomorphism classes. And then finally, inside this last isogeny class, there's this distinguished isomorphism class of the universal homogeneous one that has infinite residual rank. Okay. So this is kind of how these spaces are organized in my head. So one, I'll just close with mentioning like one question that I think might be interesting that occurred to me while I was watching the other talks. So from the additive combinatoric side, strength comes up in like this idea of bias, and it's reflected in the bias of the polynomials, is my understanding. And all these guys have infinite strength. So I guess they behave the same, at least according to some measures in additive combinatorics. But what might be interesting is like, can you distinguish these different isogeny classes by some like refined things on that side? Like you could imagine like, so here you could consider like these forms in finite many variables, which are like approximating an element of this isogeny class. And you could look at truncations of this thing, which approximate something here. And can you tell those apart somehow? Okay, well, I'll stop that.
Thank you for the nice talk. Any question for Andrew?
Yeah.
Is there a sense in which these are reductive groups?
That's an interesting question. I don't know the answer. Yeah.
Is there a Stillman's conjecture for exterior algebra?
Oh, yeah, that's not true, actually. So, I mean, the projective dimension version is just like not true because things have infinite projective dimension, but there's a way that you can recast it in other terms, and that's also not true. Yeah.
Are there like any interesting things you can say about the quotient, the cubic mod finite strength, or like what do you know about this?
And I don't know a lot. In a way, it's kind of an ugly thing. Like these infinite dimensional spaces, they're like topological vector spaces, and it's like a dense subspace. So it looks kind of bad from that point of view. I mean, this quotient sort of parameterizes, or relates to maybe the variables appearing in this infinite polynomial ring. But yeah, I can't say anything too precise. Yeah.
Does the Radon graph somehow sit inside? I mean, is there a way of in which classical Fresnel limits sit inside linear? Linear Fresnel limit.
I don't know. I think that's a really interesting question. Like you could take the adjacency matrix and try to build some tensor from it, and yeah, I don't know. But yeah, that's pretty cool. Yeah.
So this infinite orthogonal group G2 that you've written, this isn't like a limit of ONs.
It's not the union of ONs. It's like you take the infinite diagonal form and all automorphisms preserving it.
Okay. So is there like any sense in which GD is like can be expressed in terms of like finite dimensional groups?
I don't think so. I think it's just a purely infinite dimensional thing.
Does this work over any other fields?
Yeah. So this paper that Nate and I wrote works over any field of characteristic 0. You don't even need algebraically closed. This last thing on these isogenies, that works in positive characteristic 2, at least outside of characteristic 2 and 3. And yeah, I mean, there's lots of other things to say, I guess. Like this universality of strength, that's an interesting one, because that's like, you have to like find vectors of a given norm. So it looks like you're really over an algebraically closed field. And that obviously fails over the real numbers, because if you imagine like a positive definite quadratic space of infinite dimension, you're not going to embed any negative definite thing inside of that. But when I was here earlier this year, Jan and Arthur and I figured out that it looks like universality of strength does work over like any imaginary number field, like Q adjoint I. And that actually kind of connects back to this more classical stuff of like Schmidt and Birch, about like the number theory and these like high strength varieties defined by high strength equations. Like it's pretty easy to solve those equations. Yeah.
There are no more questions, then let's thank the speaker again.